talk today about something that is, I think, a kind of a true innovation relative to our technology that we kind of discovered by mistake. And the first slide I wanted to show everybody was we were playing around with a new technology that was basically trying to develop a new type of intumescent paint. As you know, is a company that specializes in performance paints and coatings. We started playing around with trying to develop the next best great intumescent paint, and when we were doing that, we started messing around with a product called Aerogel. And Aerogel was a product that is called an anamorphous silica. And if you can see that slide right there, you'll notice that this specific material is actually a highly insulative thermal product. And we thought, gee, maybe if we put this into a new type of paint, we could make it burn. I mean, maybe not burn, but maybe prevent it from burning in this new intumescent technology we were playing around with. So we started messing around with a bunch of different things, ceramics and all kinds of things, to try to make the architectural marketplace the next smoothest type of intumescent. Well, what we discovered was it didn't survive a fire test at all. And this anamorphous silica aerogel was kind of a funky material. And what we realized when we started putting thermocouples on steel plates, which unfortunately I'm sorry to show you, is this ability for this product to actually create a thermal barrier. And as we looked at it more closely, we realized that if we folded this particular silica into this resinous technology, we actually created the very first highly thermally insulative material at very low thicknesses. And why this was significant, because when you started looking at how this technology comes together, we started, I'm just going to jump forward a little bit, and when we started playing around with different resins, we realized that not only do we have a material that was highly energy efficient and a very thin film, but was also extremely durable. And so we started running a bunch of tests. This was back about 4 years ago. And we started running on this Aerolon technology, and I'll show it to you in just a second. But we realized we had to meet a couple of different targets from a coating perspective, but also from an insulation perspective. And what we're talking about now is not only does the material have a very low K value, you're talking about a K value of 0.035, which is analogous to, it's actually lower than spray foam. So this silica created a very thin, highly efficient thermal barrier. And what we started realizing was that when you started putting it into different types of resins, you got also a tremendous amount of performance and durability. So as you look at some of the testing we started running on it, 5,000 hours of cohesion and 5,000 hours of salt spray, we could actually take this film and expose it to all of these exposures, humidity, immersion, and put it in saltwater immersion and deionized water, for 2,000 hours at 140 degrees F, and we realized, boy, there's something unique here. So as we started playing around with it, we realized that we could create a systems approach to creating a more thermal efficient barrier. And what we found was it started to fit into a number of different sections in the design community. It's going to basically fall into 5 categories. It became extremely energy efficient, which means it needed less energy to keep something hot or cold. In a lot of places you'll find today what we're talking about is if I'm trying to keep a tank or a vessel or a substrate at a constant temperature or a liquid at a constant temperature, this product will do that. It can be used for a reduction of moisture formation. So if I have sweating pipes, we had a lot of people calling us already from the oil and water business saying, hey, I have sweating pipes on a lot of different structures and I want to reduce this sweating from occurring. How do I do that? And this technology led us in that direction. CUI, a lot of people don't know what CUI is, but it's corrosion under insulation. A really big problem in our design communities, whether it be heavy engineering or even commercial, is corrosion under insulation. You know, I was in the John Hancock Tower last week, and even just in a mechanical room that has sweating pipes, the amount of accelerated corrosion that occurs under insulation is pretty significant. So this technology allows a directly applied approach to the substrate, but we store concrete to eliminate corrosion under insulation. Personnel protection. We discovered that we also could put down a thin layer of this material, approximately 1/16 of an inch, and prevent people from getting burned up to 400 degrees F. So that was one of the photos I wanted to show you. And then finally, thermal breaks. We actually realized that what we created was a thermal break. Okay. So to take a little bit farther, I'm going to just jump ahead for a second. You can look at these. Can you see these photos, Mark? All right. Okay. All right.
Yes, Greg, they're fine.
Yes, thank you, thank you. So I want you to see these because we showed this recently at the National Association of Corrosion Engineers show in Houston. And what you're looking at are 3 tanks. The Aerolon tank, which is in the center, is a ceramic technology. Now there are coating technologies out there that are thermally insulative coatings. We're not the only one in the business, but what we found was we were the only ones in the more efficient side of the business. There's other types of technologies. Ceramic is one of them that has been out there for a while, but no one has been using this particular what they call anamorphous silica aerogel to do what we're doing. So we basically have these 3 tanks, and they all have the same thickness. So they're both on at 150 mils. And you can see here in this next slide, the Aerolon coating, we're showing energy efficiency here. So what we're trying to do is keep these tanks at a constant temperature. And how long does it take, or how much energy does it take to basically maintain the temperature of a liquid? And so the liquid inside these tanks is water, trying to be maintained at 160 degrees F. So when you look at how much energy was going to go into maintaining that liquid temperature, they looked at the efficiency of the thermal coating on the outside to see which one would keep it constant and for how much cost. And all the people in the oil and gas business were very interested in this because when you started looking at the Aerolon technology, which you can see is at 47.6%, the control is in the middle, which is uninsulated, and then a ceramic material out there at 22.8%, we were virtually 50% more efficient at the same thickness. So going forward, as we look at the potential energy savings of things, we now developed a product that actually showed basically a return on investment, as it were. Where we had to look at these coatings is where were they most efficient? Okay, so in the energy saving side of the equation, if you look at these two lines, the Aerolon is the lower one here. The ability for a product to become more efficient was really in its thickness was around 5 millimeters or just under 200 mils. So where we see the greatest amount of return on potential energy savings on a coating like this is somewhere between basically just under 1/4 of an inch in its ability to be most efficient. And after that, even if you added up to 1,000 mils of material or 40% more material, you were seeing a diminishing return. So these materials, even though they're highly, you can actually get an R rating. We're actually applying a project right now, a rating of a 1/2 inch thick of R2. You get these diminishing returns basically based on this chart of efficiency over 200 mils. Okay, so let's talk about condensation. One of the things that's interesting about this technology is that what I'm going to do, I'm going to just jump forward a second here so you can see this. What you're looking at is a job we did at Kraft Foods, and this is a job right outside of Boston. And what's interesting about this location is that there was foam insulation on the surface. And all the foam insulation had basically got an air gaps underneath it, had basically disbonded or that air space under it, and started getting a lot of corrosion under insulation. So in this plant, you can see in this particular location here, this room operates at about 82 degrees F on a regular basis. The room above it was operating at about 45 degrees. So when you looked at the steel temperature up at the roof, and it was sweating like crazy, all was falling into the clean product. The plant actually makes gelatin, and they would find condensation running off into the finished product. So we came in and we applied Aerolon over the whole surface at 120 mils. What we did, we calculated the amount of dew point, temperature, and humidity, came up with a design thickness that would eliminate or greatly reduce the potential of condensation from forming in this location. So what we're doing is we're applying the coating directly to the steel substrates in all of these locations. And unlike a conventional insulation, whether it be foam or mineral wool or some other form of insulation, you have it directly applied to the substrate. Now think of this technology as kind of like moisture vapor drive under a slab. Under vapor mitigation issues, you have moisture penetrating up through a concrete slab. It basically reaches a certain pressure that blows off the finished material. Well, and what they do is they put down moisture vapor mitigation technologies that basically don't stop, but slow the migration of moisture so slowly through the films that it doesn't blow off a finished flooring product. Well, the same thinking takes place with aerogel materials. The Aerolon technology basically is slowing the transfer, and I'll show you that shortly, slowing the transfer of temperature so it never reaches dew point. So if we can slow down the temperature change from cold or hot to a surface, that's why you can put your hand on this material up to 400 degrees F at basically 60 mils or 1/16 of an inch thickness without burning yourself. That thermal transfer is happening so slowly that you never reach temperature. In this particular case, you never reach dew. Okay. Next conversation obviously is corrosion and insulation. The key contributor to CUI is moisture egress into the insulation, which obviously when you get moisture in your insulation, you automatically lose 60 to 70% of your insulated value. The traditional insulation will fail from jacketing, accelerating the CUI. So when we get air and moisture underneath insulation, we get an accelerated corrosion effect taking place. Moisture that accumulates and condensates under that is a driving force behind the CUI. This is a huge problem in pipelines. It's a huge problem in just mechanical spaces and power facilities where you get these blowouts from insulation that you can't see where the corrosion's occurring. This approach with the Aerolon basically eliminates that. And when we talk about CUI, you're looking at really corrosion or piping insulation is a huge one. The JPI came out with a Materials Performance Magazine, which is the basic magazine for National Association of Corrosion Engineers, which I think is interesting and worth noting. The absorption of those 4% water by volume to dry insulation can increase the thermal conductivity as much as 70%. So when you have those kinds of numbers, just a little bit of moisture can make that a huge problem. So we think that there are advantages to looking at a directly applied solution. So if this were a very typical power plant or a refining operation or even a mechanical space in a building where you have insulation, any place you have an air gap, you're going to have CUI issues. Okay, the next one is going to be personnel protection. We look at this as obviously a huge factor, and I was just in a power plant early this morning on a project we're involved with, but they have a huge amount of steam pipe. And talking with AECOM and Stantec, a number of heavy engineering firms, their issues are numerous, but they also look at the personnel protection of a technology like this. So if I could apply a product directly to a hot steam pipe that might be up to 350, 400 degrees F, that I can provide personnel protection that doesn't come off the pipe, that is a huge advantage. So this technology will allow you to do that. And you can also apply it up to 200 degrees while the pipe is still hot. So this is a totally LEED material. It's all water-based primers, all water-based technologies. The Aerolon is water-based and water-based finishes. So you can apply these things on hot substrates and get basically a whole approach to, sorry, I'm getting rid of some emails here, whole approach to personnel protection. in terms of an
So
entire
Greg,
system.
Greg, this means that 5-second contact time means that you could put your hand on it for 5 seconds and not burn it? Or why 5 seconds? Is that just an industry standard for safety, or?
Yeah, the industry standard is 5 seconds. We're actually good up to about 40 seconds for this technology. So you can leave your hand on the surface for greater than 5 seconds. That's what the ASTM standard, I think it's C518, requires. But that's the industry standard is 5 seconds. So if you're leaning up against the pipe, you're feeling it getting warm, but you're not getting burned. That's where I would go with that.
Thanks.
Okay. So here's just an example of that, where you have a sample of the Aerolon coating directly applied to a hot panel. It's at 157 degrees C, which is about 300 degrees F, and you're actually seeing a hand being applied, someone putting their hand on it. So this is very typical of what we do in a lot of applications, whether it be for steam or hot liquids or hot tankage, even piping in mechanical spaces and office buildings that we're using this on now. And inversely, we're using this for condensation or sweating issues. Okay, so we started looking at, when I was with a friend of mine, Wagdy Anis, who's with Wisconsin Elsner, about 2 years ago, I mentioned to him what we were doing with this technology, and he looked at me and he said, you don't know what you have here. And I said, well, educate me. He said, we have a huge problem in the thermal bridging business in the structural side of the world, and what you described here is a very ideal kind of thermal break or a thermal bridge, which addressing a thermal bridging issue. So we started actually running. He suggested we get a hold of a firm called Morrison Hirschfeld, and we started running a bunch of different thermal breaks. But before we go there, let me just talk a little bit about how this technology actually works in comparison to other forms of insulation. And I think this is a really good slide that kind of illustrates what we're talking about. So here you have gas molecules and a conventional insulation on the left. And you're looking at something that's 200 nanometers in depth. So if I have 200 nanometers of insulation, this is what the air molecule speed would be mimicking in that particular environment. So I have lots of air gas molecules moving around. So when I put my hand on this, on the top of this piece of pipe or this structure, I get a very fast transfer of heat. I get burned, or in a lot of cases, I'll get cold if it's very cold. If you look at on the right side, where you see the aerogel particles with the Aerolon particle, the Aerolon technology, with the aerogel particles, you can see at the very bottom of the slide, the molecules are moving quickly, and as they start going up through these chambers, now that's what the anamorphous silica aerogel does. It builds these microscopic chambers so that as gas or hot or cold molecules of air can't move around fast enough. So imagine, if you will, at the very top of that, you can see they're virtually idle. So this is what we talk about when we talk about the transfer of heat or cold is occurring at such a slow rate because they get caught in these chambers of the anamorphous silica and therefore don't translate to hot or cold at the very top of this. So you can see if I were using this in a thermal break condition and I had a cold steel temperature, let's say at minus 20, and I was trying to slow the migration of temperature, by the time I get to the very top of the film, the amount of air movement or air temperature in a room would be so you'd be probably up to almost within the dew point, not within the dew point, that you never form condensation. And that's where this comes into the reduction of heat and cold, is slowing these molecule transfers down. Okay, so we went to Morrison Hirschfeld and started looking at this technology as a way to actually say, gee, do we have a thermal break or a thermal bridge material that could go on here? We started looking, or I should say Morrison Hirschfeld broke this entire scenario initially for 8 particular details, which I'll walk you through. But they were broken up into 4 basic subsections, as it were. We had structural steel beams with bypass thermal insulation, we had structural subgirts, clips and attachments, steel stud assemblies, and then thermal bridges at floor slabs and balcony decks. Those are the 4, we kind of said, well, let's just look at these and see what the numbers come out looking like. So we started doing some actual modeling. And which was interesting, the results were, if you look at a thermal break material, I would just use, as an example, a Fabrica pad, which is very common in the world of thermal breaks. People want to use structural breaks on jobs, or structural engineers do. They'll use like a Fabrica pad, a sandwich between something to create a thermal break. This technology, this is where the thermal conductivity comes in important play here. If you have a thermal conductivity of 0.035, which is very, very low K value, a Fabrica pad, as an example, has basically a thermal conductivity of about 400. Okay, and so the difference between those materials is almost 1,100%. Or I should say that's wrong. It's 1.57. So when you look at the delta between those two, is 1,164% difference in performance. So we started plugging these thicknesses into different types of thermal structural elements. We started seeing some really interesting data. So if you look here on the right, this is detail number 1. I'm just going to walk you through 8 details kind of quickly, not spending a lot of time on them, but just so you can see them. So here, the Aerolon is the actual tube coming through this wall, kind of like a canopy structure that would be penetrating a facade. And if you look at that on the right, so there, it has the effective R value, has the BTU, has a % difference in the surface temperature, which is an indication of condensation effect. We ran these to 3 different thicknesses, 60, 120, and a half-inch thickness, just to see what it would look like. And the R values of these at 60 mils was 0.24, and R value at 120 is 0.5. Which Jenny, when they saw this, they said, we've never seen a thermal break that actually had an R value associated with it. So when you started plugging in these thicknesses into the decals, you started seeing not a negative number that you would see with a typical, piece of neoprene or wood or a piece of, shim plastic, like a Fabrica pad as an example. Those would be in the much more negative side of the scenario of percentage difference. We actually started seeing positive numbers on the energy efficiency side. When we started looking at a lot more of these details, we found that we were actually seeing energy savings, meaning we're not getting to the point of condensation. And this one here, you can see just that clip angle, that beam going through. We're at 0.7 on the surface temperature index at 60 mils. Well, 3.1% difference between the effective R value and the U value, obviously, but it's a very significant difference in the ability for this product to prevent condensation. And that's what Jenny was so interested in, is could they put a coating on the perimeter of a building that could slow transfer of energy, cold or hot, into a building that they could prevent condensation from forming. So all of these details, they're obviously all here. I don't want to spend the entire time going through all of them, but the data is pretty interesting.
Hi, Greg. It's Mark. If you could go back to one slide to detail 3. So the Aerolon coating is actually on the Z-girts that penetrate through the what appears to be blue insulation, and you don't have to worry about, and so that creates your thermal break?
Yes, that is what you see. Anything that has beige, the beige color there, that is where the Aerolon has been applied in this particular application to metal studs, right? And actually, just you can't see it here, that's just on the exterior fascia of the metal stud. It wasn't the entire metal stud. So just the outside strips, that 3 inches, is what you're actually coating there.
So if you have a cladding system that was held off by Z-girts, once you put in the insulation, potentially you could just add the Aerolon coating and then screw your cladding to it and it would perform?
Correct.
Wow. Okay. Thank you.
Yep. I want to take you to, just going to, I'm sorry, that one, detail number 5, too, Mark, just so you can see that one too is the exact same thing. With the flange of the metal studs. I was wrong. The other one was fully coated. This one was fully coated. Sorry. This is the one I thought I was looking at. So that one here, which is even more interesting, I think, is it's just the face of that interior insulated metal stud applied to the exterior flange. So that one was even more interesting. And I looked at the numbers and I'm like, wow, at 60 mils, we're even better in terms of thermal bridging than we were on the previous one. One I thought was most interesting, which was significant, which everybody has a problem with, is this one here, with brick shelf angles. I mean, everybody has this on virtually every building you do, just about. And look at the numbers here. At 60 mils, we're seeing a 12.5% savings in terms of actual energy loss. So when I look at the temperature surface index, anything that Morris and Hirschfeld told us that anything really above like 0.68, 0.7 was trending really great for no formation of moisture. And you get above 0.8, it's like it's a moot point in a lot of cases. So this was a very interesting detail, and this one here too is not quite as good, but actually still very good in terms of its actual thermal efficiency. These are.
So, Greg, sorry to interrupt again. So in other words, if you get condensation on a shelf angle, eventually you get exfoliation and you start pushing your brick or your precast off the building. I've certainly seen that a lot. So you're saying there won't be condensation. The R value is just an added bonus, but there won't be condensation?
There won't be condensation that forms, because if you look at these numbers, you're above, it's just like an air barrier mark. Anything above 0.8, anything above 0.8 is it's really dry. So we're not reaching that condensation point at all in these locations. And this was run in the northern hemisphere. So this was trying to take the worst case scenario. We kind of took this and said let's apply this in the most aggressive applications we can in terms of actual modeling. And
so if you were looking for a 100-year building, this would stop the problem of the brick shelf exfoliating.
Exactly. Now you have to also remember, go way back to the performance data. We had to look at this and say, not only do we need thermal efficiency, it's got to be durable. So I can immerse this in water and still maintain this thermal efficiency. One thing I haven't talked about is the ability of an anamorphous silica gel, aerogel, to repel water. I can take a little portion of this aerogel, sprinkle it on my hand, dip my hand in water, and pull it out, and it's perfectly dry. So you can imagine when I put this in a building environment for 100 years, and if I can keep something from sitting on a surface or sitting on a substrate, I have a very corrosion-resistant material. So that's why it had to be durable. It had to be could take a lot of abuse, salt spray, exterior exposure. You can leave this technology exposed directly to weather, and it will not, yellow and shrink and do all the things like typical insulation would do. So that's kind of a story on thermal breaks, which we're doing much more modeling with this right now, and we'll have a lot more to tell going forward. But this is obviously a very big subject that we're focusing on.
And Greg? Oh,
yeah.
This is Matt. One question from the audience here. Brian asks, will there be, do you know of any compatibility issues between the aerogel and the typical peel and stick flashings used on brick walls?
We're actually testing with bituthane right now as an example. We have, I will, basically, we're in the middle of testing it right now because we've actually been approached by people like W.R. Grace to say, gee, is this something that we might be able to put on bituthane direct? We actually can stick this material to different types of fabrics and other types of materials that we're experimenting with right now.
As far as you know, an oil-based or asphaltic material doesn't corrode the coating?
No, it shouldn't. It's totally water-based in that respect. So we won't have any corrosion effect that takes place with this. This is basically a single component material that is spray applied, and once it gets cured down, it's relatively hard, firm material. So flexible.
And the material, I would assume, it's not the type of thing that has tensile strength because it's just a coating. You wouldn't lap over a silicone sheet, or you'd probably see this on a metal substrate, not on top of a bituthane.
No, I typically would put it, well, we're testing both, to be honest. We're testing it underneath bituthane and on top of bituthane.
Okay.
Because we have had luck using this different types of insulative fabric, as an example. We're doing a bunch of things with the U.S. Navy and a number of other places, but it's one of those things where...
And are the oldest applications 2 years old yet, or?
Yeah, oh yeah, the craft project we did over 2.5 years ago. We have a number of others which I'm going to show you in a second here that are obviously completed projects on a number of different applications.
Thank you.
Yep. I just wish this photo here is really very typical of what I would term as a thermal break issue. So what we did was we were trying to demonstrate this at the Green Show in California this past year. So what we did was we took a window frame. We created basically, we sandwiched it between, we took a cooling line and sandwiched between two window frames. And so we created a sweating window frame, as it were, that you might see in an older building that was built in the 70s or 80s. We're actually underway with a project like this right now. So what you're looking at on the right side is the aluminum window frame that is now sweating because it's a cold temperature that's looped in there. I think the temperature of that 42, 47 degrees, something like that. And now we have the ambient temperature outside in the room that's 75 degrees F or whatever. And you're seeing the sweating occur. On the half side that you see past that screw head is now coated with basically 40 mils of Aerolon. And we have no condensation that has occurred. So what you're looking at, this is very typical of what I believe is a kind of a revolutionary approach to solving a lot of sweating and condensation issues, especially in thermal bridging applications, is a virtual elimination of condensation through this technology. Now, if you can imagine, that window frame is at 42 degrees, and the inside temperature is what's causing it to sweat. So if I put on Aerolon at that thickness, and I'm slowing the migration of temperature to the point where it never reaches dew point, that is the benefit behind this approach. So this is why we think we have a pretty significant avenue to pursue with how to reduce condensation effect, especially in cavity wall construction where, you know, obviously we do get that occurring presently. Yes, there are other technologies out there. I just want to mention the ones that are probably the most prevalent. You're looking at a ceramic bead right here, and that's primarily where I showed you those tanks before that had you know, the three tanks, so the ceramic versus the aerogel particle treatments. And the difference between these is that they're not that efficient. The K value of the beads is obviously a lot less than that of an aerogel. So you're looking at the milliwatts, Kelvin per milliwatt at 50 to 100, whereas aerogel at 12. This is where you get that efficiency. So at the same thickness, you're going to have to put on 50% more of a ceramic technology that has more, obviously, cost and time and labor and everything associated with it versus one coat or one lift of the same thickness in an Aerolon technology. So that's primarily just driven by the fact that the thermally insulative technologies are totally different and are more efficient. So this is just kind of a comparison of the two. If you looked at the Aerolon in 3 coats versus a 13 coat with the same thickness in terms of efficiency. So, okay.
Oh,
just some case studies, and then I'll take some questions.
So yeah, Greg, there was just one question quick before I know you go any further. The slide that had the sweating window on it, a couple people pointed out that it appeared as if there was still water on the metal strip below, even under the side that had the Aerolon technology. Can you explain, was that just a result of how you had to set up the window to make the element, or was there condensation that was happening that was dripping below the coating, or just trying to figure out the reason for that?
Sure, yeah, that's actually not dripping from the blue component. That is an uncoated aluminum panel that was part of the exterior frame. So we didn't coat that portion of the panel. So that's not dripping from that. That's actually, it's sweating all by itself below that.
And Greg, with the screw headed to the left, so that's, I believe I've seen Aerolon coatings that appear smoother than that, or is this the typical appearance?
Very typical appearance of an Aerolon, as it were. And we're the first, really, the Aerolon. This is the first one out of the box, as it were, from an aerogel perspective. So there's been
okay. And how is the bevel? And how is the bevel around the screw head achieved? Was that cut?
Oh, they did that.
Putting in.
Yeah, they were putting it in to show it you know, between that little artistic scenario there where they wanted to show the screw head obviously sweating, but the things around it not sweating. So we just, that's where we cut the line. We just created a little bevel there. Any other questions there, Matt?
I have two questions that I think I'm going to wait till the end and let you do the case studies first.
Okay. Okay, so what we also looked at, well, this is a couple of projects that we've actually completed. This is in Cooperstown water treatment plant. And this is a very big problem in the water business. They have open-top filter tanks that 1,200 square feet, condensation issues in the summer months, and you get cold water coming in from either the ground or from a lake. Deep lake, you get a lot of sweating that takes place. So we had an ambient condition of 85 degrees, surface temperature 35, and RH is 75. And what they were constantly having was this, what happened there? Oops, okay. So here's the kind of before and after of the corrosion of the CUI. So here's the CUI issue that they had and the coating applied directly to the piping. Now, what this does in the CUI configuration or use is that you can actually see where your corrosion is going to occur now if you have a problem. Under the one on the left, you have no idea where the corrosion is taking place. You can see at the very top of the pipe there's a lot of heavy corrosion taking place there where sweating has occurred, and look at the mold that's growing underneath it in the belly of it. So we have a lot, yeah.
So the reason the insulation was placed on the left was to slow down the condensation, not necessarily for R value. So on the right, because you've stopped the condensation, you don't need the R value. Is that, am I correct?
No,
or would you still put more on?
Well, here's a very interesting approach. There are places where people want to just put down 30 or 40 mils of Aerolon directly on the pipe, and then if they need more insulation, they're adding rigid insulation or other forms of insulation. But now you've stopped the CUI issue. So if we can stop the CUI from ever forming, the water from forming underneath, in this particular case, they were just doing this to eliminate the sweating on these pipes. So now they've taken off all the insulation. They're now putting Aerolon on the whole plant inside this application, and that's where it's being utilized. If you wanted to add more insulation on top of this because you wanted to achieve a very specific R value, the Aerolon can give you up to 1 or 2 if you wanted it to, and then you could add more to it. Personally, I think that we were seeing more people interested in applying this as a CUI prevention issue and then adding insulation if they needed more.
Thank you.
Okay, so here's Crystal Lake water treatment plant where they have a huge amount of equipment that's sweating all the time. And this is where we applied Aerolon to this entire pipe chase and piping gallery to eliminate that from occurring. And this was a very extensive project where we're seeing a lot of this done now even in normal mechanical spaces. So this essentially eliminates condensation from occurring and sweating from occurring. And is the finished product, already finished painted, as it were. And now they have no more insulation coating these pipes, no more falling off, none of it dripping. And so the client is pretty happy with how this came about.
And Greg, is it integrally coated, or is this a green over some other color?
No, this is I'm sorry. We put a fish coat of our 1028 or 1029 on top of this. So yes, so this is a paintable. Aerolon all by itself is kind of like a yellow coating.
Okay.
And then we can top coat it with any color that you look for. Yeah. Also, when we're doing, this is a Cabot, we did a Cabot plant where they had a pelletizer that was operating around 400 degrees F. So we are applying this directly to a lot of OEM equipment now, especially hot equipment. Alcoa is very interested in this, as there are a number of the other Alcan, people like that have a lot of hot equipment in these smelters in Canada. So we can actually apply this directly to an OEM piece of equipment or tankage. And this is, I like to show this photo because you can actually block out the areas where bolt heads take place. And the amount of thermal transfer that takes place there is pretty minimal. So we can actually do blockouts there very successfully. So this is a piece of equipment that's operating very hot. and now at least people can come up to it and not worry about getting burned against it. In a meat rendering plant, this is a recycling tank that's obviously operating at fairly high temperature, and again, this is just another application of where we're putting things like this. Now, this technology can also be applied to concrete. In fact, I've been talking to LeMessurier consultants about using this in different thermal break applications on concrete edge details for slab and balcony decks. So instead of using structural thermal break technology, which can be very expensive, up to $100 a foot or so, we're going to be using Aerolon in lieu of it in a lot of cases. So I'm showing you a lot of steel projects right now because that's kind of what I had at my disposal, but this can also be applied to concrete. Okay. That's basically the summation of this presentation, and I'm more than happy to take any questions, Matt or Mark, that you have coming in.
Great. This is Matt. We have two questions from the audience right now. One of them, Richard was mentioning that in the presentation you had talked about a study by WJE, and was wondering, is it possible to get a copy or even just a condensed version of those findings? Is that something that's available on the Aerolon site or something?
Yeah, if someone wants to send me an email, Matt, that would be fine. I can send the report to them. We're getting ready to run a lot more tests and then post the results, but I'd be more than happy to send it. It's actually Morrison Hirschfeld out of Vancouver, and with a recommendation by Witz Jenny to have them run the 3D modeling, because they are running a very large ASHRAE study for the Canadian government, and the Aerolon is going to be folded into the ASHRAE study for thermal efficiency and thermal bridging. But I'd be more than happy to send it if someone can get my email, get an email to me. I'll be more than happy to send to anybody.
Okay. And to everybody, note that I did put Greg's email in the chat box, so you should be able to see that and copy that if you'd like to get a hold of Greg for that information. A couple more questions popping in here, but one more that was already waiting. I wanted to wait till the end because I think it's something that might be information for everybody. Brian Clark asks, what's the warranty or the life of this aerogel material when it's applied to metals or other substrates?
Sorry, could you repeat the question one more time? It broke up right in the middle of it.
Sure. What is the warranty or the life expectancy of this aerogel material when it's applied to metal or other substrates?
We look at, we warrant the system for 5-year material. So we have found that this material sticks to a lot of different things we never thought it would. Remember, you're not putting on a paint. That's a very important distinction. It is not going to go on and be rigid like a paint. This, if you were to have a sample of it, if you press down hard enough, you could put your fingernail into it. So it has a little bit of give and flexibility. It's an acrylic base, single component acrylic. It has acrylic, I'm going to show you the video, but acrylic top coats and also acrylic water-based epoxy prime coats for steel and for concrete. But the guarantee, the warranty is a typical TMIC 5-year material warranty. And if there is a unique substrate other than steel or concrete or something else that someone was looking to try, we would more than happy to test anything that someone would have. But it goes on with a very low pressure spray pump, kind of the same pump that they use. It's called a GTX 2000 by Greco. It's the same pump that they use to spray textured ceilings in hotels. So it's a very easy material to install. But adhesion to different substrates and steel and concrete should be in excess of 10 or 15 years. I've had on this job at Kraft, which was probably the most aggressive place I've put it, because they pressure wash everything in there. So they're using 3,000 psi pressure washing as a regular diet in a lot of these environments, and water splashing on it all the time, and taking a fair amount of abuse. And that's been it's almost 3 years now, and it's perfectly intact. So hopefully that answers your question.
Great. We do have a few more questions popping up here. So the next one comes from Maribeth. She's wondering, is this product by any chance nearing availability for commercial buildings? She has some clients with block walls that would enjoy having insulative coating on interior block walls. I guess just a little bit about the availability of the product currently.
This is commercially available for the last 2 years. So I mean, we're selling this every day, all day. This is not a new technology we're just coming out of the box with. This is something we're actually actively selling presently.
And to find out more information, do you guys have wholesalers, distributors, or is it more a contact directly through the site to learn about purchasing?
Yeah, if you're looking for direct contact, you could contact your TNEMIC company directly. They'll put you off to where you are in the country. TNEMIC works through a series of independent reps throughout the country. So if you're Alaska or Boston, there's a rep that handles that territory. So the TNEMIC would be able to redirect you if you go to tnemic.com.
Okay, and I'm going to do there's a follow-up question here from Linda that just popped in. Since it is available for purchase, is there a requirement that there has to be an approved form of application or an approved applicator has to have any kind of certification or anything for doing it, or is it something that you could possibly give to a painting person to be able to apply with successful results?
We say with anything you should have a trained installer. We just don't like to willy-nilly give materials to anybody just to kind of throw on. So we would always prefer, it's not a difficult material to install, and probably a lot of people with the right training could do it. But it's always been TNEMIC's, TNEMIC's the last privately held family-owned paint company in the United States. We're a very conservative family approach to a lot of things. So we would always prefer to say, hey, contact your rep in this area. I have an Aerolon installation potential. Who could you recommend? And we can give them a list of people that have already installed it and been trained. It's not a certified applicator program, but we prefer trained people to install it.
Okay. And then going to a little bit more in detail questions here. Larry has a question. Can the product be sprayed onto the interior surfaces of an extruded aluminum frame and still prevent the condensation on the exposed surfaces to the frame? So I guess it's much more of a, if you could...
Yes, we're actually doing that right now on 2 buildings for Boston Properties here in Boston, where they had buildings that during this past winter just sweat like crazy because they get these thermal bridge problems. And so we're spraying this directly to aluminum window frames on the inside of a building to solve that problem.
Okay. And then another question here from Richard. Do you by any chance know if the Aerolon meets the 2009 IECC requirements for pipe coverings by itself? Currently states that the 503.2.8 requires a minimal of 1.5 inches of normal insulation, but allows for adjusted thicknesses for other materials. That is a question
I have not answered, so I can't honestly tell you if we do or don't. There's a guy at TNEMIC by the name of Andy Hoffman. Reply to Hoffman@tnemic.com that could answer that question. I don't have that one, and I don't know the answer to it.
All right, that is the last of the questions I have. Mark, I'm not sure if you have any.
Well, the issue that came up before a little bit about effective R value, once a lot of the building codes changed and you had continuous insulation outside of your metal studs, as is recorded in a lot of northern states, there was an effective R value issue as opposed to the insulation that was in the stud cavity, where every 16 inches there was metal as a thermal bridge. So it sounds like some of the values here that were, and I believe ASHRAE has a formula for effective R value. So again, Greg, you're not really selling it for the R value, but it seems to have a very high effective R value.
Right. You know, it's funny. When I was with Jenny and I said to Wagby, I said, Wagby, tell me the number. What's the number get to be for an R value for a thermal break? And he said, there is no R value because no one can ever provide an R value in a thermal break. I said, so if I gave you an R value of 0.24, well, what does that do? So when we went to Morris and Hirschfeld and we said, let's run it at 0.24, 0.5, and at 2, and see what the math comes out looking like. No one had ever come up with a thermal bridge material that not necessarily tried to save energy, but was to prevent. I look at the whole thermal bridging issue as a prevention of condensation. And that's what Jenny was, and so was Simpson, Gumperz, and Hager so interested in, because they're trying to prevent moisture and molds from gathering inside a lot of these cavities. Right now, they have nothing in a lot of places. So if they can stop heat or cold transfer from condensating in a wall cavity, that's really where I believe this technology solves a tremendous amount of problems. Not that we're going to...
Well, I agree with you, because it's the part of the wall that takes the weather and the stress between the inside and outside temperatures, and many buildings, their life is shortened to 10 or 15 years because they haven't solved the thermal issues and the condensation issues. And for people who want a building that will last as long as possible with our current technology, it seems you're onto something pretty good.
Yeah.
Any more questions, Matt?
Yeah, there's a follow-up from Larry. I think I may have just asked the question wrong. He was wondering, with the aluminum surfaces, is there any way that you'd actually be able to spray the product on the unexposed interior surface of a frame so that the exposed exterior surfaces could still be seen as aluminum but still prevent the dew point issue?
Yes, absolutely. We're actually doing that with MIT right now on a very large window replacement. We're actually putting it on the back side of the window frame as they put the new windows in. So yes, as long as you can apply this, I would prefer it in that application where you don't you have it on the back side of the aluminum frame.
And I think the question was, if there was a frame, however, that was a U, could you put it in the pocket of the U instead of on the outside of the U, so you wouldn't see it either? Okay, yes. So the answer is yes.
Yes, you could. Yes, you could.
Okay.
Okay. Well, great. That looks to be all the questions we have at the moment.
Well, Greg, any closing thoughts? I just really thank you for taking the time to share this technology with us. I think it fits very well with the goals of the Sustainability Practice Group, and thank you very much.
Well, thanks for having me, and I'm glad at least we could show you kind of a new technology we discovered by mistake. Has always been kind of fun.
Thank you, Greg, and thank you, Matt, and please tune in next month.
All right.
Bye now.
Thank you, everyone. Bye.